Chapter 6. Let us look at some interesting facts about light in the chapter Wonders of Light, Part 1. So, let us begin. Once Harshad visited a laughing gallery in a fun fair. There was a variety of mirrors in the laughing gallery. He observed different and funny images of himself in the mirrors and laughed. Many questions arose in his mind. Why is it not possible to see the distorted images in the mirrors at home? How is it possible in these mirrors? Let us study about it. First, let us study about the mirror. A mirror is a reflecting surface. Every day, you use a mirror to see yourself. It is a plane mirror. A plane mirror is a plain glass sheet having one side coated with a thin layer of silver and painted by red color to protect the silver coating. Another variety of mirror is a curved spherical mirror. It is a part of the spherical reflecting surface. Its cross-section is an arc of a circle. It is generally made up of glass. One surface of glass is silvered to make the other surface reflecting. If the inner side or concave side of the spherical surface is polished, it is a concave mirror. The light is reflected from an inner surface. It is also called as converging mirror, as rays parallel to the principal axis after reflection converge at a single point. If the outer side or convex side of the spherical surface is polished, it is a convex mirror. The light is reflected from the outer surface. It is also called diverging mirror, as rays parallel to the principal axis get diverged after reflection. Concepts related to spherical mirrors. 1. Center of curvature C. The center of sphere of which the mirror is a part is its center of curvature. 2. Pole P. The center of the spherical mirror is the pole. 3. Principal axis. The straight line passing through the pole and center of curvature of mirror is its principal axis. 4. Optical center. The central point of the mirror on the principal axis is its optical center. 5. Focus of concave mirror F. The rays parallel to the principal axis get reflected from the mirror and meet in front of the mirror at a single point. It is the focus of the concave mirror. 6. Focal length F. The distance between the pole and the focus is called focal length of mirror. The focal length is the half of the radius of curvature. Let us learn about light. Have you tried this? Stand in front of a mirror. Observe your image. Close all doors and windows of the room. Also, switch off the light in the room. Now can you see the image? Why? No, we cannot see the image because there is no light. Observation of images in various mirrors is related to light. It is only due to the presence of light that all of us can enjoy various natural wonders like sunset, sunlight, rainbow, etc. The beautiful world around us includes green forest, colorful flowers, blue sky at daytime which becomes black with twinkling stars at night. We also see different artificial objects in the surroundings only in the presence of light. Light is a form of electromagnetic radiation that produces the sensation of vision. We are able to see any object when light rays from that object enter our eyes. Such an image, formed by converging of rays at a point, is a real image. The real image can be obtained on a screen. The image made by a plane mirror is a virtual image. This image is formed at a point from where the reflected or refracted light rays appear to diverge. This image cannot be projected on a screen because the rays do not actually meet there. Let us look at the concepts convergence and divergence. Activity. Take 5 sticks from a matchbox. Arrange the sticks in such a way that their chemical-coated ends are meeting at a point. Here, the chemical-coated ends are converged. Now arrange the sticks such that the other ends are together and the chemical-coated ends are away from each other. Here, the chemical-coated ends are diverged. When light rays meet at a single point, it is convergence of light. When we want to concentrate light at a point, converging beam of light is used. Doctors use this type of beam to concentrate on teeth, ears, eyes, etc. Converging beam of light is also used in solar water heaters and other devices. When light rays from the same point source are spread away from each other, it is divergence of light. When we want to spread light from a source, diverging beam is used. Example, in street lights, table lamps, etc. Convergence and divergence of rays by concave and convex mirrors are shown here. Let us see how images are formed by a concave mirror. Take a large shining metal spoon. Bring it deeper, that is, concave surface closer to your face. Can you see your image? We can see an upright and magnified image. Now take the spoon away from your face. What change do you observe in the image? The image becomes smaller and smaller. Now repeat the activity by turning the convex surface of the spoon to the front. What changes do you notice in the image? We can see an upright and smaller image. The nature, position, and size of the image formed depend upon the distance of the object from the surface. Images formed by a concave mirror can be studied with the help of ray diagrams. A ray diagram is a specialized pictorial representation used to trace the path of a ray of light. For drawing ray diagrams, rules based on laws of reflection are used. Rule 1. If the incident ray is parallel to the principal axis, then reflected ray passes through the focus. Rule 2. If the incident ray passes through the focus, then the reflected ray becomes parallel to the principal axis. Rule 3. If the incident ray passes through the center of curvature, the reflected ray traces the same path. The ray diagrams for the formation of image by a concave mirror for various positions of the object are illustrated here. Summary of image formations is given in this table. Let us look at the sign convention for reflection by spherical mirrors. According to the new sign convention, the pole P of the mirror is taken as origin. The principal axis is taken as x-axis of the coordinate system. The sign conventions are as follows. 1. The object is always placed on the left of the mirror. 2. All distances parallel to the principal axis are measured from the pole of the mirror. 3. All the distances measured to the right of the origin are taken as positive, while distances measured to the left of the origin are taken as negative. 4. Distances measured perpendicular to and above the principal axis are taken as positive. 5. Distances measured perpendicular to and below the principal axis are taken as negative. Let us look at the mirror formula. When we measure distances according to sign conventions, we get proper values of object distance, image distance, and focal length. The object distance, u, is the distance of object from the pole. The image distance, v, is the distance of image from the pole. The focal length is the distance of principal focus from the pole. The relationship between object distance, image distance and focal length of a spherical mirror is the mirror formula. The mirror formula is given as 1 upon V plus 1 upon U is equal to 1 upon F. This formula is valid in all situations for all spherical mirrors for all positions of the object. Magnification by spherical mirror. Magnification produced by a spherical mirror is expressed as the ratio of the height of the image h2 to the height of the object h1. It gives the relative extent to which the image of an object is magnified with respect to the object size. The height of the object is taken to be positive as the object is usually placed above the principal axis. The height of image is to be taken as positive for all virtual images. However, it can be taken as negative for real images. Let us learn about lenses. In which instruments have you seen lenses? In instruments like projector, solar heaters, camera, binoculars, spectacles, we see the lenses. A lens is a transparent material bound by two surfaces, out of which at least one surface is spherical. A lens having both spherical surfaces bulging outward is a convex lens or double convex lens. It is thicker in the middle than at the edges. This lens can converge light incident on it. So it is a converging lens. A lens having both surfaces curved inwards is a concave lens or double concave lens. It is thicker at the edges than at the middle. This lens can diverge light rays, so it is a diverging lens. Let us look at the concepts related to lens. Any of the above lenses has two spherical surfaces. Each of these surfaces form a part of a sphere. 1. Center of curvature C. It is the center of the imaginary sphere which forms the given lens. Each lens has two centers of curvature, C1 and C2 respectively. 2. Principal axis. It is an imaginary straight line passing through the two centers of curvature of lens. 3. Optical center. The central point of lens on the principal axis is its optical center. When a ray of light passes through the optical center of a lens, it passes without undergoing any deviation. 4. Principal focus of convex lens F. When several rays of light parallel to the principal axis are incident on a convex lens, they converge at a point on a principal axis. It is the principal focus of the convex lens. Figure 6.7a. Every lens has two principal foci. 5. Focal length F. The distance of principal focus and optical center of the lens is the focal length. Let us perform this activity. To determine approximate focal length of a convex lens, take a convex lens. Place it between the screen and distant object like a tree or a building. Move the lens towards or away from the screen till you get a well-defined image on the screen. Can you guess at which point you get the image? Measure the distance between the screen and the lens. The distance between the screen and the lens is the approximate focal length of the lens. Let us look at the images formed by a convex lens. Let us do this activity. Take a convex lens. Determine its approximate focal length as per the previous activity. Place the lens on a lens stand. Place it on the central line such that optical center of the lens lies just over the line. The two lines on either side of the lens correspond to f and 2f of the lens respectively. Mark them with appropriate letters 2f1, f1, O, f2, 2f2 respectively. Place a burning candle in different positions on one side of the lens. 1. Far beyond 2f1 to the left. 2. Just behind 2f1. 3. At 2f1. 4. Between f1 and 2f1. 5. At f1. 6. Between f1 and O. Every time, obtain a clear, sharp image on the screen on opposite side of the lens. Record the position, relative size, and nature of the image, and you will find the same results as given here. Images formed by a convex lens can be studied with the help of ray diagrams. Ray diagrams are useful to study the position, relative size, and nature of the image formed by lenses. Following are rules for obtaining images by convex lens. Rule 1. If the incident ray is parallel to principal axis, then the refracted ray passes through focus F. Rule 2. A ray of light passing through the optical center passes through the optical center undeviated. Rule 3. If the incident ray passes through the focus, the refracted ray becomes parallel to the principal axis. The ray diagrams for the image formation in a convex lens for different positions of an object are given here. Let us look at the sign conventions for lens. The focal length of convex lens is positive and that of concave lens is negative. Optical center of lens is taken as origin and principal axis of lens is taken as x-axis. The sign conventions for lens are similar to the sign conventions of spherical mirror. Only care should be taken to apply appropriate signs for the value of object distance, image distance, focal length according to the type of lens, object height, and image height. Lens formula. The relationship between object distance u, image distance v, and focal length f is lens formula. Here, distances should be measured according to sign conventions. The lens formula is given as 1 upon v minus 1 upon u is equal to 1 upon f. The lens formula is valid in all situations for any spherical lens. Let us now see magnification by a lens. The magnification produced by a lens is the ratio of height of the image h2 and the height of the object h1. Magnification produced by a lens is also related to the image distance v and object distance u. Let us see what is meant by power of lens. The ability of lens to converge or diverge light rays depends on its focal length. Convex lens of short focal length bend the light rays through large angles by focusing them closer to the optical center. The degree of convergence of light rays achieved by convex lens is expressed in terms of power of lens. It is the reciprocal of the focal length. SI unit of power of lens is diopter. If focal length is expressed in meter, the power of lens is expressed in diopter. Therefore, 1 diopter is the power of a lens whose focal length is 1 meter. 1 diopter is equal to 1 upon 1 meter. 1 upon V minus 1 upon U is equal to 1 upon F. Functioning of lens in human beings. Activity 6.6. Have you seen a photographic camera? Compare the human eye with it. State similarities between them. Photographic camera and eye have lenses that can focus and project an image of the object they are looking at. Pupil from human eye can expand or contract to adjust the amount of light that enters. This is the same as the shutter of a camera. The cornea acts like a lens of a camera. The iris and pupil act like the aperture of a camera. State the point of differences between them. Eyes work in harmony with your brain to create the images that we perceive, whereas camera is just an instrument which projects an image which depends on the camera apparatus. In human eyes, the lens changes its shape to focus. In camera, the lens moves closer or further to focus. The amount of light entry in the eye is controlled by the iris, while in camera, the amount of light entry is controlled by the diaphragm. Let us study about human eye. The human eye has a thin membrane known as cornea. The light enters the eye through the cornea. Maximum refraction of light rays entering the eye takes place from cornea. Behind the cornea, there is a dark muscular diaphragm called as iris. The colors of iris are different for different people. There is a small opening of variable diameter at the center of iris called pupil. The pupil is useful to control and regulate the amount of light entering the eye. The pupil contracts if there is too much light, while the pupil dilates in insufficient light. This tendency of pupil to adjust the opening for light is called adaptation. The cornea forms a transparent bulge on the surface of the eyeball. The eyeball is spherical in shape with a diameter of about 2.3 centimeters. There is a transparent biconvex crystalline body located just behind the pupil. It is a lens. This crystalline lens provides fine adjustment of focal length. With the help of this adjustment, real and inverted images get formed on the retina. The retina is the light-sensitive screen. It is a delicate membrane. It consists of large number of light-sensitive cells. These cells get activated upon illumination. They generate electrical signals. These signals are passed by optic nerves to the brain. Then the brain interprets these signals and also processes the information in such a way that we perceive the objects as they are. The functioning of lens is very important in human eye. The eye adjusts to various object distances by changing the focal length of lens. For normal eye, in relaxed position of eye muscles, the focal length of eye lens is about 2.5 centimeters. The second focal point of eye lens is located at the retina. In this position, normal eye can form sharp images of objects located at infinite distance. At this time, the lens is thin and distant objects are clearly seen. The focal length of eye lens decreases while viewing the nearer objects and the lens becomes thick. This gives a sharp image of nearby objects on the retina. The ability of the lens of adjusting focal length is known as power of accommodation. The process of focusing the eye at different distances is called accommodation. This is brought about by a change in curvature of the elastic lens, making it thinner or fatter. But focal length of the eye lens cannot be decreased below a certain value. We cannot read the words in the book if it is held very close to our eye. The minimum distance from the normal eye at which the objects can be seen clearly and distinctly without any strain on the eye is known as the distance of distinct vision. It is about 25 centimeters for normal human eye. Let us look at the problems of vision and their remedies. Some people cannot see the objects clearly due to loss of power of accommodation of eye. The problems of vision are related to various reasons like weakening of ciliary muscles, change in size of eyeball, irregularities on the surface of cornea, formation of membrane over the eye lens, etc. Because of refractive defects of eye, the vision becomes blurred. There are three common refractive defects of vision. Let us study about them. Myopia or nearsightedness. It is the defect in which a human eye can see nearby objects distinctly but is unable to see distant objects clearly. In myopia, the image of distant object is formed in front of retina. There are two possible reasons of myopia. A. Ciliary muscles do not relax sufficiently, converging power of eye lens becomes high. B. The distance between eye lens and retina increases as eyeball is lengthened or lens is curved. A suitable concave lens can correct this defect. This lens causes light rays to diverge before they strike the lens of the eye. The power of concave lens is so chosen that it creates required divergence, and hence after the converging action of eye lens, the image is formed on the retina. The focal length of concave lens is negative, so the power of spectacles for myopic eye is negative. Depending on the degree of defect, the power of concave lens is different for different eyes. Hypermetropia or long-sightedness. It is the defect in which human eye can see distant objects distinctly but is unable to see nearby objects clearly. The image of near object falls behind the retina. Two possible reactions of hypermetropia are A. Weak action of ciliary muscles cause low converging power of eye lens. B. The distance between eye lens and retina decreases on account of either shortening of eyeball or flattening of lens. In this case, focal length of the eye lens is too long. This defect is corrected by using convex lens. The rays coming from nearby objects are first converged by convex lens and then converged by eye lens to retina. Depending upon the degree of defect in the eye, power of convex lens is different for different eye. As the focal length of convex lens is positive, the power of spectacles for hypermetropic eye is positive. Presbyopia. It is also called as old age hypermetropia. The power of accommodation of eye usually decreases with aging. The near point of aged people recedes and they find it difficult to see nearby objects comfortably and clearly without spectacles. As ciliary muscles lose the capacity to change the focal length of eye lens, aged people experience eye lens presbyopia. Sometimes they suffer both myopia and hypermetropia, and then the person needs bifocal lens. In bifocal lens, upper part is concave lens to correct myopia and lower part is convex lens to correct hypermetropia. The concave lens is useful for distant vision and convex lens for near vision. Nowadays, refractive defects can be corrected by using contact lenses or through surgical interventions. Applications of spherical mirrors and lenses. Concave mirror. 1. In torches and headlights, the source of light is placed at the focus to obtain a parallel beam of light. 2. In floodlights, the source of light is placed just beyond the center of curvature. 3. Reflecting mirrors for projector lamps. The object is placed at the center of curvature to obtain an image of the same size. 4. To collect heat radiations in solar devices, heat radiations from the sun coming from infinity is brought to focus by concave mirror in its focal plane. 5. Shaving mirror or dentist mirror. It produces an erect, virtual and highly magnified image of an object placed between its pole and focus. 6. Solar furnaces. Large concave mirrors are used to concentrate sunlight to produce heat in solar furnace. Convex lens. 1. Simple microscope. A simple convex lens of small focal length can be used as a simple microscope. A magnification of about 20 times is obtained by simple microscope. Watch repairers, jewelers, etc. use it. 2. Compound microscope. A combination of two convex lenses having short focal lengths are used in compound microscope. It is used to observe bacteria, viruses, cells, microorganisms, etc. 3. Telescopes. A combination of two convex lenses is used in telescopes. An astronomical telescope is used to get detailed view of astronomical bodies like planets, stars, etc. Terrestrial telescope is used to study terrestrial objects. 4. Optical instruments. Convex lens are used in different optical instruments like camera, projector, spectrometer, etc. 5. Spectacles. Convex lens is used in spectacles to correct defects like hypermetropia. Well, that ends the chapter. Hope it was a joyful learning. You have the options to view a mind map for a quick recap and a question and answer section to study the exercises. Wish you all the best. Bye till we meet again.